Thanks, Karina. So now that we all know what groundwater is and how it moves down into the ground, let's explore how it moves through different Earth materials. Years ago, all of Waterloo was buried underneath a huge glacier that was hundreds or even thousands of meters deep. It was roughly equivalent to 4 CN towers tall. That is a lot of ice. Now, these glaciers were dirty. They were full of sand, gravel, and other stuff. And about 12,000 years ago, that ice melted, and as it did, the stuff trapped in the ice, remember the sand, the gravel, and the clay, was all sorted into layers, hundreds of meters thick. This model is very similar to what is below our feet in Waterloo region. So here are some of the wells. Here's the river. This would be like the Grand River. Here's the lake. This might be like the lake in Victoria Park. And this is the stuff underground. These are artificial structures that we put there. Now there are several layers in this model. At the surface, this green stuff is meant to represent vegetation. So that would be the plants and the grass, the trees. And below that layer, there's some coarse gravel, and then some fine sand, and then some coarse sand. And wedged in there, there are some clay layers. If we were to follow well 1 all the way down, you'd notice that it runs into something, and this is meant to represent the bedrock. In Waterloo region, the bedrock is dolostone and limestone, and it's highly fractured, and these lines represent those fractures. In some places, like Lower Gorge, the bedrock is near the surface, and you might see this if you went for a walk in that area. But in other places, it is hundreds of meters underground. This is a core of the bedrock from Waterloo, and you can see here that there are fractures, and in these fractures, this is where the water is held and where it would flow. This is what makes it an aquifer. Of course, sand and gravel also hold water and allow it to flow, so these are also aquifers. Some material, like clay, is exceptionally slow at letting water flow through it, and so we would call that an aquitard. It's slowing the flow of water. All right, so now we get to do the fun part. We're going to show you how water flows through this system, and to do that we're going to use dye. I'm going to invite my assistant over, and she's going to actually apply the dye. So everybody, this is Alba, and we're going to give her the syringe. Here's our blue dye, and she's going to squeeze it and suck some blue dye in, and she's going to add a little bit to each one of the wells, these first ones here. Go for it. Yeah. The height of the water underground is what we call the water table. So in here, you can see, because Alba's added blue dye to all these different wells, we can now see where the water table is. I'm going to use this red pen, and I'm going to connect the river to the depth of the well, the water in the wells, to the lake, and we'll see visually where the water table exists. And what you notice is that it's not a flat line, that it follows topography to some extent. The depth of water underground changes depending on where you are. That's pretty important if you're a farmer or if you live in the country and you need to get your water from underground. You want to know how deep the water is, so you know how deep you're going to drill. The height of the water underground also changes with time and with precipitation. And at the top here we've got a pump that's pushing water through our system, and it's over here on the right in our area of recharge. This is where the water, when it's raining or when the snow melts, water enters the ground. So right now it's raining. If I move the pump over, it stopped raining. And you can see, you should see in a second, the blue is going to start dropping in each one of these wells. So as the rain decreases, the amount of water entering the system decreases, and the amount of water underground decreases. So here you can see it's well below that red line. And it's going to keep dropping the longer we leave it off. Of course, it'll eventually rain again, so let's bring this back. And wow, look how fast that is. There's a good rain event, a nice thunderstorm. The ground is going to quickly recharge. One of the other things that I thought we should explore with this model is how the water enters the system over here, but it exits over here in the river. So this water is flowing from one side to the other. Now, we've got several different layers, several different aquifers. The water is going to flow through them at different speeds because of the pore spaces, because of the size of the material. So the gravel, it's pretty big material, and that means the spaces between those materials is quite large as well. So in theory, if the spaces are larger, the water is going to flow faster through that. Up here in the sand layer, the particles are smaller, so there's smaller spaces between the particles. That means water can't flow quite as fast through it. So if I was to guess which of these 4 layers the water is going to flow the fastest, I would guess that the fractured bedrock is going to be the fastest because the pore spaces are the largest. And this fine sand layer at the top is going to be the slowest because the particles are so much smaller. There are other layers like this clay layer. They're going to act in a different way, but we'll come back to that in a minute. So I'm going to add a little bit more dye, and then we're going to flush it. We're going to see which one flows the fastest. Now remember, our theory is that the water's going to flow really fast in this one. And look, follow Alba's finger. It's already flowed almost all the way to the other side. Number 2, it's only about halfway. And in number 1, in this one, it's only moved a little bit, maybe 2 centimeters. So the size of the material is really important for how quickly the water flows. And fractured bedrock is the fastest, fine sand is the slowest, and then these cobble and gravel and coarse sand, they're in the middle. All right, so we've cleaned up the flow model, we've flushed it out. It's nice and clean now. We're going to show you one more thing with this flow model. In Waterloo Region, we get most of our drinking water from underground. And it's important that we don't contaminate it, that we don't put something in it that might make people sick. Unfortunately, it's hard to imagine how we could pollute the ground and the groundwater because it seems solid. But it is possible to put stuff into that groundwater that we don't want to drink. And a flow model like this is a great way of showing you how that can happen. So let's do that now. All right, so we've zoomed in so you can see this part of the model better. This is where the artificial structures are. In our model, we have a septic tank, which we're not going to get into, and then an underground storage tank. This is something you would find at a gas station. And this is where the gasoline is stored that we put into your cars. Now, unfortunately, sometimes it can get a hole in it, and if that happens, that gasoline is going to leak slowly into the ground. I'm going to use red dye to demonstrate this. So in our example, red, it would be the gasoline. Okay. So as I add the red dye, I want you to think about where it's going to go underground. Okay, so put it in the chat. Is it going to end up in the septic tank? Is it going to end up in the lake? Is it going to come out in one of these wells? I think it might make it all the way over into the river. Wow, look at that. So it's moved all the way over into the river. Now the river is turning red. So that gasoline that leaked out of the underground storage tank was able to flow down and deep underground, flow all the way down into the river. Incredible. Some of you might be wondering though, why didn't it go down into the coarse gravel layer or into the fractured bedrock? So if you think you know the answer to that question, put it into the chat. You might be wondering, is there anything we can do about this? If an underground storage tank leaks, and we don't want the oil or whatever the contaminant is to get into the river, how can we clean it up? Well, thankfully, we have these wells. Perhaps we can use a well to clean up the contaminant before it gets in the river. So let's flush this model out. We'll contaminate it again, and then we'll use well 5 here and we'll see if we can't suck the pollutant out before it gets in the river. Okay, now while that starts to flow, we're going to use this syringe with this tube here to act as our pump. And we're going to connect it to well 5, and we're going to draw water up out of this gravel layer here. And we'll see as the plume gets closer, we'll see if we can't suck it up and keep the contamination from getting in the river. So it looks like if we can keep pumping, we can pull contamination out of the ground before it gets in the river. What's happening is this well is in the middle of what we call a plume of pollution. Because we know which way the water's flowing, we can predict which well we could use to collect the wastewater. Now, I haven't been pumping quickly enough because a little bit of the waste has ended up in the river, but a lot less than if we'd done nothing. You can see how the pink is getting less and less. The water is getting cleaner. So you can also pump from the site where the contamination is entering the system, and you can add clean water. And this is what scientists would call pumping the water out and treating it and then returning clean water back to the system. Well, I hope you enjoyed this amazing aquifer and learned about how water flows through different materials. Think about this model during the next activity. Bye everyone.